Okay. Okay, so there's a nice graphical representation for posets. Okay. So before I can get to that, I need a definition. So if S and T belong to P, we say P is a poset, of course. We say that T covers S. We're defining what the meaning of the word cover, and this is sometimes denoted S less than, but with a dot T. If S is less than T, okay, and there exists no element U such that S is less than U is less than T. In other words, T is in some sense immediately bigger than bigger than S. So there's nothing in between which there's nothing intermediate. Okay, so this is called covers, and this is known as a covering relation. Okay, so now I'm in a position to define the graphical representation. Just 1 second. My laces are out. Sorry, I keep tripping over my lace. Okay. So, alright. So now the graphical representation we can talk about. So here's the definition. The Hostler diagram of a poset P is the graph whose vertices are the elements of P and whose edges are the cover relations. By convention, if T covers S, then S is drawn below T. So remember that a graph consists of vertices and edges. It's again a very abstract object. So the vertex set for us will be the entire poset itself, and you draw an edge between two elements if one of them covers the other, and by convention the lower guy is drawn below. So again it's good to do examples. So again examples. So okay, so let me first give you some show you all possible posets pictorially with 3 elements. So all possible posets with 3 elements. Okay, so there are not too many of them. I'll keep them unlabeled so that it's not too large. There is always the boring poset on any cardinality where there are no relations. Well, if there are no relations, then all of these properties are vacuously true because there is nothing to check. Okay, so then that poset consists of no order relations. There's nothing is ordered with respect to anything. So you would draw them all on the same level, disconnected. There will just be 3 points. So it's a graph with no edges. Then you can have a poset with 1 order relation. So this guy is less than this guy, but this guy is unrelated, is incomparable with either of those guys. So you cannot say, so if I were to call this A, B and C, A is less than B, but you cannot say that A is less than C or C is less than A. They are incomparable. That's the term used. And similarly, B and C are incomparable. Okay, so then we have, you have the poset where there are 2 guys at the bottom and 1 guy at the top. So this guy, so again, if I were to number them, label them, C covers both A and B, but A and B are not comparable. Okay, the converse can happen. You can have things like this, A, B, C. So just for completeness, let me label these also. So A is covered by both B and C, and there is the totally ordered set, just like the example on the of the integers, where A is less than B is less than C. So if you pick any 2 elements, we know which is. So these are all possible posets on 3 elements. Okay. In this extreme case, so this is one extreme case which is totally ordered. Everything, any 2 elements are comparable. This is the other extreme case where this is unordered, totally unordered. No 2 are comparable. Okay. So both of these are in some sense boring, but all the interesting things are happening in between. Okay, so let's come back to the examples here, and let me draw the Hostler diagrams so that you see some interesting posets other than these ones. So let's look at B3. So remember, Bn is the power set of 1 to n, and the relation is containment. So let's look at B3. Okay. So what is the smallest element of B3? Well, it's the set which cannot be contained in any other set, right? What is that set? Well, that's the empty set. So for B3, I have at the bottom, remember the smaller elements are drawn below, so I'll start from here. At the bottom we have the empty set. What is this? What is the cover relation? So any set, any non-empty subset of 1, 2, 3, so this is 2 to the 3, which is the power set of 1 to 3. So any subset is larger than the empty set, because the empty set is a subset of any non-empty subset, any non-empty set. But what is the cover relation? The cover relation means there cannot exist anything in between. So therefore, if you want to go slightly above the empty set, you have to have a set with 1 element. So there are 3 possibilities. So there's 1, there's 2, and there's 3. So we will draw edges between this. Okay, actually it might help if I draw black lines as edges. Okay, and then we have, by the same logic, I'll have 2 element subsets of 1, 2, 3, and finally I'll have all of 1, 2, 3. So let's draw the cover relations. Let's draw the edges in this graph. So 1 is less than 1, 2. 1 is less than 1, 3. 1 is not less than 2, 3. Because 1 is not contained in 2, 3. Okay. So these two are actually incomparable. 2 is less than 1, 2. 2 is less than 1, 2, 3, but not with 1, 3. Similarly, 3 looks like those, and all of these are subsets of 1, 2, 3. So if you stare at this picture a little bit, you can see the cube. And this is going to be the general property of Bn. The Hostler diagram of Bn will be the n-dimensional cube, looked at in the proper way. Okay? So, and this will play a part very soon. Okay, let's do another example. Let's say D12. So it's pointless to take numbers which have very few prime factors, because otherwise the POSET is boring. So here, what's the smallest number? So here for Dn, remember, I is less than or equal to j if I divides j. The smallest guy or guys will be those which cannot be divided by anything. There's only one such number, which is 1. So, 1 is at the bottom. Right? Now 12 is 2 squared times 3. So it has 2 prime factors. So they will be the cover relations. So let me now draw the edges. So I'll have 2 and 3. These are the 2 distinct prime factors of 2. And this will be covered. And then what are the other prime factors? Okay, so as a set, what is this? This is 1, 2, 3, 4, 6, 12. Okay, so what is going to be there above 2? Well, both 4 and 6 are going to be above 2. But 6 is also going to be above 3. And finally, 12 is going to be above everybody. So let me draw the cover relations. Okay, so it looks nice. Okay. Yeah, okay. So this is this is sometimes called the divisibility POSET, I think. Okay. Anyway, there's some name for it. Okay. So now you get some idea of how to construct, how to visualize a POSET in terms of the cover relations by drawing this Hostler diagram. Okay. So before I get to the main result, maybe I should tell you about something about POSETs. So there are lots of properties, that algebraic properties one can prove purely at the POSET theoretic level, because POSETs have such minimal requirements, but yet one can build up a lot of machinery for POSETs, and one can prove various properties like I'm going to do at the level of POSET. So it's very, very vast generality. Okay. So one nice class of POSETs that often come up in the literature are what are called lattices. So let me define them. Before that I need another definition. So for S and T in P, an upper bound is an element U satisfying S is less than or equal to U and T is less than or equal to U. Right? It's just some number which is larger than both S and T. So this is again analogous to what one sees for the real numbers. And just like for the real numbers, one can define the notion of a least upper bound. A least upper bound or join, this terminology is specific for posets of S and T, is an upper bound U such that every other upper bound V of S and T satisfies Q is equal to. So in other words, it's the smallest possible upper bound. This is known as the join, and it's denoted SVT, and this is read as S join T. This is the upper bound if it exists. Okay, this need not exist, but if it exists, it's denoted as. Similarly, the greatest lower bound or meet is denoted as this caret T, read as S meet T. Okay, so again, this is the opposite. This is the largest guy which is smaller than both S and T. Okay. Okay, so for real numbers we have this property of upper bounded sets having a supremum and things like that, which you might have seen. So these ideas even extend at the POSET theoretic level. So let me just let me now define lattices. So a lattice is a poset L for which every pair of elements has a meet and a join. In other words, I take any two elements, I can find the least upper bound or the meet and the join exist. Okay, so just to show you that they may not exist all the time, so I mean not everything is a lattice. So a counter example to say that everything is a lattice, if someone believes that, is to take, well actually this is already an example, because if I take two of these elements, they don't have a meet, okay, or a join, right? There's nothing, but they don't even have upper bounds. But a more interesting example is the following poset. I take four elements with this Hostler diagram. So if I take A and B, C is an upper bound for A and B, D is another upper bound for A and B, but the criterion for least upper bound is not satisfied, because C and D are incomparable. Okay, so C and D are upper bounds of AB, but C is not less than or equal to D, and D is not less than or equal to C. Okay, so this is not a lattice. Okay, all right. So okay, so posets are a very general class of objects. Lattices are slightly more special, and one can say some things about lattices, but not about posets. But okay, maybe that will take us far afield. So let me end with this, with the statement of the Mobius inversion formula in full generality, and I'll show you a proof also, which is quite elementary. Okay, so this is the Mobius inversion formula. So this has the same name as the Mobius inversion formula for in the number theoretic setting, but it's much more general. Okay, so remember when we were talking about the number theoretic example, we had defined this Mobius function, which was 1 if at integers which had which were square free and which had an even number of prime factors. It was -1 if it was square free and had an odd number of prime factors. It was 0 in all other cases. Similarly, we are going to define a Mobius function here for any poset. So, but the definition is a little more complicated. So, the Mobius function of a poset P is a function mu from P cross P to R. Let's say it's not necessary to have it on R, but it's okay for our purposes, satisfying the following properties. Mu of SS is 1 for all S in P. Okay, it takes two arguments. So the way you should think about this is the left argument should be less than the right argument. That point will come in a second. So mu of S U, if I have mu of S and U, this you define recursively as the sum over all T in P such that S is less than or equal to T is strictly less than U of mu of ST. Okay, for all S less than U in P. So if you have two elements such that the left guy is smaller than the right guy, you define it recursively. You sum over all possible smaller guys, and each time you will get a sum over something where the gap is going to get smaller. So this will be a finite sum. Okay, so this will work. And mu of SU is equal to 0 if S is not less than or equal to U. This can happen in two ways. Either S is greater than U or S and U are incomparable. In either case, we do not define this guy. Okay? So let us compute the Mobius function. So let us compute in this example the Mobius function. So mu of, and we'll always take S to be the empty. Okay, so mu of phi comma some set S. Let's compute this. Okay, so what is mu of phi? By the first property over there, mu SS is always 1. So this is going to be 1. So in the circle in black, I'll write the Mobius function. What is mu of phi 1? To do that, to compute that, we have to use the recursive formula. Okay? So we have to sum over all t's in between the empty set over there and 1, but not including 1, and I'll have mu st. So this is minus mu of what? T can only be the empty, right? And S is empty anyway. So this is mu of empty, so that's minus 1, right? So this guy for 1 it's minus 1, and there's nothing special about the set 1. I could have done it for 2 or 3. So all of these guys it's minus 1. Okay? Now let us compute mu of phi 1, 2. Okay. So now when I'm looking between phi and 1, 2. I have to know mu of phi with all these guys, which I already do. So this is going to be minus of, when I look at that, my t is going to be either phi 1 or 2. So it's going to be mu of phi 1 plus mu of phi 2 plus mu of phi minus of the whole thing. What is this? So minus of mu of phi 1 is minus 1. So I have minus 1 plus, let me put brackets here, again minus 1 plus 1. So I have minus of minus 1 plus 1. So if you check it out, it will be 1. Because this will cancel. And there's an overall minus. So for 1, 2 it is 1, and you can see by similar calculations that for 1, 3 it's going to be 1, and 2, 3 also it's going to be. Okay, and the last bit is to calculate for this. So now the idea is clear. So when we were calculating for 1, 2, we looked at all the guys below 1, 2. So now we have to look at all the guys below them, sum all of them, and take the negative. So what will we get? 1 plus 1 plus 1. So 3 ones, 3 minus 1s, and a 1. So the total is 1, and I have to take a minus. So this is minus 1. So this is how one calculates the Mobius function. This you can do for any POSET, and you can take the left guy to be anything, but it's convenient to take it to be the lowest guy. So the remarkable thing I would like you to observe is that the Mobius function for this example always takes values 1 and minus 1. Not even 0. It only takes values 1. Okay? But if you did the computation for, so let me do it quickly for this POSET. So maybe I'll divide it. Okay. So for this POSET, let's calculate mu of 1 and whatever element. So for 1 it will always be 1. For 3 it will be 3 and 2 it will be minus 1, just by the same argument as before. For 6 it will be 1. But for 4 I will have to sum all the guys below 4. There are 2 of them. Their sum is 0, and so the negative of that is 0. So I'll actually get a 0. And for 12 I'll have to sum all these guys. So I have 1 minus 1 minus 1 1. So I have a 0, and then I have adding a 0. I am taking negative of that. So I'll again get a 0. Okay. Okay. So I want to come back to this example later. Okay. But anyway, so I hope I've given you some idea of how to compute it. So now let me state the important theorem about the Mobius inversion. The Mobius inversion formula. Okay. By the way, I should stress that all this time we have been working with, most of the time we have been working with finite posets, but some of these results also generalize to infinite posets of a special kind. But for finite posets, certainly everything that I'm going to say is true. Okay, so let P be a finite poset. And f and g be functions from P to R, satisfying which way? G of t is the sum over all s less than or equal to t of f of s. Okay, so this should remind you of the number theoretic property that we had. Again in the Mobius inversion formula. Then, so this theorem is the Mobius inversion formula. I'm not writing it again. Then f of t is again the sum over all s less than or equal to t of mu st g of s. Okay, this is a very powerful generalization, as I will explain very soon, of both the inclusion-exclusion formula and the number theoretic Mobius inversion formula. And the proof is elementary, actually. So if you look at this formula, so if I rewrite this formula, if I take this sum on this side, you see that this term over here is exactly this thing when t is equal to u. So here we had taken s less than or equal to t less than u, but the only term that we are missing here is mu su, and that's over here. So if I take everything over here, this is equivalent saying that the sum over all t in p of s less than or equal to t less than or equal to u mu of st is 0. Okay, this is how the Mobius function is defined, right? Okay, so that we are going to use in the proof. So we want to prove this. Let's start with the RHS. So what is that? So I have sigma s less than or equal to t mu of st g of s. What is this equal to? I'll just substitute for what g of s is. Okay, so this is sum s less than or equal to t mu of st, and now I need another letter, so this is g of s. So let's say sum r less than or equal to s f of r. Right? This is just the definition of. I've just used g of s. Okay, so here I have sum from s for s less than or equal to t. Here I have some r less than or equal to s. I'm going to interchange the sums. Okay. So this is for a fixed t. Remember, the sum here is over s. Here the sum is over r. So now I'll first go over all r less than or equal to t. R has to be less than or equal to t by transitivity of the order relation. R is less than or equal to s, s is less than or equal to t. So r is less than or equal to t. Okay, then I have f of r. This does not depend on s. Now I have the sum over all s. But where does s live? S is clearly greater than or equal to r. S is clearly less than or equal to t. So that's the only constant. So I have r less than or equal to s less than or equal to t. And this is a sum over s. Of what? Mu st. Right? So if you look at that formula over there, this guy has to be 0. unless R and T are the same. Because if S were equal to did I write something on here? Right, the sum is over T between S and U, right? The sum is over T between S and U. If U were equal to S, then I only have mu SS, that is 1. So this is 0 if S is strictly less than U. That's what I have here actually. Yeah. So I'm restating. So this sum, this is non-zero only if T equals R. By definition of the Mobius function, nothing more than that. But if T is equal to R, then what do I have here? R is forced to be T, so I get Ft. But that's the left hand side. Okay. So this ends, and it's such an elementary proof. So the complication was in coming up with this definition of this Mobius function. And now let me quickly connect with the two motivating examples that I have, and I have done the computations over here, and this will be the last thing that I will say. So when we wrote down the inclusion-exclusion formula, when we wrote down the general formula for the principle of inclusion-exclusion for the cardinality of the union of AIs, then we had some plus ones and minus ones. We had first sums of cardinalities of AIs, then minus the sums of cardinalities of AI intersection AJ, plus the sum of cardinalities of AI intersection AJ intersection AK. And those ones and minus ones are precisely what you see over here. So you'll always have 1 at the bottom, you'll have minus ones at the next level, then you'll have ones at the next level, minus ones at the next level. This will always go on. And this is where the fact that I told you that the Mobius function takes values plus and minus 1 only for this POSET comes into play. So the principle of inclusion-exclusion has these coefficients which are pluses, ones and minus ones. They are a special case of the Mobius inversion formula corresponding to the POSET Bn. Okay. For the number theoretic example, the POSET is exactly Dn, and there the Mobius function remember was 1 for square free numbers with even number of prime factors, and minus 1 for square free numbers with an odd number of prime factors, and 0 otherwise. You can see this exactly going on here. For primes 2 and 3 it's minus 1. For a square free number which has 2 prime factors, 6, it's plus 1. These two are not square free, they have 0. And this is precisely the Mobius inversion formula in the number theoretic setting. So now you can see the vastness of this formula. This holds for any POSET whatsoever, any finite POSET whatsoever, and two special extremely powerful results correspond to very special classes of POSETs. One is Dn, one is Dn. But this holds in much more generality, and it's extremely useful in all kinds of settings, from combinatorics to geometry to representation theory. It's an extremely useful tool to have. So, and this rests on this very abstract setting of partially ordered sets. So there are many theorems that one can state for partially ordered sets which are useful in other contexts, because this is such an abstract idea. So with this I think I'll end my talk.